supermassive black hole mergers before and after.
Great. Thanks, Francois. So as we said, I'll be talking about supermassive black hole mergers, but specifically the phases before and after and what signatures we might hope to see from them. So first we'll start by talking about pairs of supermassive black holes and the observational constraints that we have on them currently in different stages and throughout their evolution towards merger. And then I'll talk about some modeling that I've done, specifically focusing on narrow line signatures from supermassive black hole pairs at kiloparsec scale separations. And in specific, I'll discuss the kinematics of those kiloparsec scale binaries, or kiloparsec scale pairs rather, and their double peak narrow line signatures as a result, and also the lifetimes of these double peaked narrow line phases in relation to the observations of such AGN that have been recently used to find candidate AGN pairs. And then I'll talk about recoiling black holes, so the phase after the black hole merger, when the black holes, via asymmetrical emission of gravitational waves, give a kick to the merged black hole. And I'll review the observational constraints that we have on that. And then I'll talk about some work that I've done with simulations to constrain the dynamics and the lifetimes that we could observe these as offset AGN, and some possible effects on the host galaxies. And in the last few minutes, I'll talk about a specific case of a candidate recoiling AGN, which is also a candidate AGN pair. Both scenarios have been proposed, and I'll discuss some modeling that I've done to try to constrain those scenarios. So we can divide up the evolution of supermassive black hole pairs into several phases. So in the largest scales, there's the phase where the galaxies are inspiraling towards each other. The black holes just follow what the galaxies do. But if these galaxies are interacting and feeling AGN activity, then we can see pairs of quasars or pairs of AGN, and seeing more of them than we expect from galaxy clustering gives us evidence that there might be merger-induced activity. And then when the galaxies finally start to coalesce, then the black holes start inspiraling to the center of the merger remnant via dynamical friction, and then you can form a pair of supermassive black holes that is still not gravitationally bound, but is orbiting on kiloparsec scales, or maybe tens of kiloparsec scales in these merging galaxies. And then on much smaller scales, the black holes will actually form a gravitationally bound pair. This is on parsec or subparsec scales. And that, of course, is the closest to the actual phase where we would hope to see them eventually merge. They still have a ways to go before they get to the regime where gravitational wave emission takes over their evolution. But signatures of these are fairly hard to find. So I'll just review each of those. In the inspiral phase, as I said, we can hope to see evidence of excess clustering on scales of hundreds of kiloparsec up to a megaparsec, which is what's been done by Kanami et al., etc. They find that something like 0.1% of the quasars are inbound pairs. And more recently, there was a survey done looking for pairs of galaxies, or pairs of AGN rather, in merging galaxies on smaller scales, so 5 to 100 kiloparsec scales. And this study by Liu et al. Found that something like 4% of all AGN were in pairs on these scales.
Is there a sense for how this depends on the luminosity? Clearly, there must be some strong luminosity dependence.
Right.
You have two interacting galaxies, each has a supermassive black hole in the center, and at some level there will be AGN.
Sure. So I would say that the lower you go in luminosity, the poorer the constraints are on the AGN populations in general. And certainly for these largest scales, the quasars are really what they're looking for. They're very high redshift systems for the most part. These are more moderate luminosity AGN, so pushing it a little bit lower, not the total quasar regime, but certainly things are, there's a lot of contention about what exactly fuels AGN activity when you go to lower luminosity.
But there's not going to not get to say finding the power law, dependence of finding refraction on luminosity or something like that.
Yeah, I think there would still be large uncertainties. Yeah, it depends a lot on your selection criteria. So then the next phase of evolution on kiloparsecs to about 10 kiloparsec scales, there's been recent work showing that about 0.1% of these, give or take, at least are in AGN pairs. And that is the work that's been done by looking for double peak narrow line signatures. And so that's what I'll be mostly talking about in discussing the modeling of them. So AGN surveys revealed that about 1% of AGN have double peaked with 3 lines with separations of a couple hundred kilometers per second. And so the picture that one might imagine is that you have 2 narrow line regions around black holes that are at kiloparsec scale separations, and their orbital motion might produce a double peaked narrow line that you could see in the spectrum. So that's the motivation for looking for AGN pairs in these systems based on the spectral signature. And so several surveys revealed consistent results. And here's just a couple of examples along with SDSS images. Most of the SDSS images don't have good enough resolution to really tell what's going on, with a couple of notable exceptions. But then follow-up imaging has been pretty successful in actually identifying some of these as good dual black hole candidates. So what qualifies as a good candidate is one that has some evidence of a resolved, or at least marginally resolved, double lobe structure in a stellar image. And then if you put a slit along that double lobe structure and see that the spectral offset aligns with the spatial offset, then that's good evidence that maybe there is actually a kiloparsec scale pair in the system. Still not 100% clear, and certainly more follow-up observations, especially in, for example, X-ray bands, could help confirm the double nature of these AGN, but I'll talk more about that later. And then for the other large fraction that don't show the good evidence of being a dual black hole, there are some that are ambiguous, and there are plenty that just show a very regular structure and seem to be just produced by gas kinematics. So certainly a lot of them are just produced by rotation or some other features in the gas. So I want to draw your attention to one recent observation, which is currently the only possible bridge between the kiloparsec scale AGN pairs and the parsec scale. So there's this recent paper showing evidence for a double black hole, a double AGN, with a separation of 150 kiloparsecs. So when they looked in this is a 3 to 6 keV band, and 6 to 7 keV. So when they went to the harder band, they found evidence of this double lobe structure. So, we'll wait for follow-up observations to see what they reveal about the nature of this source, but the analysis they did of the X-ray imaging and the different spectral bands, they're pretty convinced this is actually an AGN pair. And so this is the only one on hundreds of parsec scales, sort of bridging that gap in the evolution of the black holes. So just to recap, there's about 0.1% at least in AGN pairs on these scales, and one resolved system as a candidate on hundreds of parsec scales. And then at the smallest scales, so parsec or subparsec scales, things are a little messier. So there's one good, very good candidate, one might even say this is better than a candidate, this binary black hole with a separation of 7 parsecs. So that is actually in the gravitationally bound beam, and it's very well resolved with this VLBI data, and that is the only one we know. There was a large survey completed recently to look at archival radio data and see if there are any more of these, and they scanned thousands of systems and basically had no results. So it seems to be a very rare thing to have 2 radio loud AGN on these scales in the galaxy merger. And then on subparsec scales, on subparsec scales, there are a couple of candidates with varying degrees of uncertainty as to their true nature. There was a recent study by Recoil et al., which found 14 candidates of AGN that have offset broad lines in their spectra, and looking over a time baseline of years, they saw motion of the centroid at a statistically significant level. And so, obviously, to really determine whether there's a binary there, you need to see periodicity in the motion of that centroid. But these are now candidates. Problem is, it's unclear, whether some of these could be produced just by outflows or could even be recoiling systems for some of them. So it's very hard for this regime to pin down the nature of the sources precisely.
What are the ultimate periods of those systems?
I think they would be years, typically, maybe tens of years for some of them. So if we keep looking, it's not impossible that we would be able to see periodicity eventually, but it'll take time. So to recap, at the largest phases of in-spiral, we're probing the early merger phase, so it's unclear exactly what the connection is between the AGN fueling and the merger activity. And at the small scales, the binaries are very difficult, if not impossible, to resolve, and the spectral signatures are, for the most part, ambiguous. So I'm going to argue that based on that and the recent success in identifying candidates on this kiloparsec scale regime, that this is currently the most promising avenue for studying black hole pairs. And so that's what I've been focusing on with some simulations that I've been doing recently, using SPH simulations with Gravitational Wave, which contains prescriptions for star formation, black hole accretion, and feedback. And so I simulate galaxy mergers that contain gas, stars, dark matter, and accreting black holes, using fairly high spatial and mass resolution to try to resolve the narrow line region as best we can. And then I have a semi-analytic model of the narrow line region that I construct in post-processing using the gas properties and kinematics as well as the black hole accretion rate. So just to describe a little bit of how that works, first, estimate the ionizing photon production rate just based on the luminosity calculated from the accretion rate, and then choose the SPH particles around the black hole that satisfy that they have a non-zero mass in the cold phase of the multi-phase ISM model that's in Gadget, and that the total covering fraction of the cold clouds within those SPH particles is less than unity, and that the particles have reasonable ranges of gas density and ionization parameter. And then once those particles are selected, then I can just calculate the H beta luminosity of the narrow line emitting clouds that satisfy those conditions using a simple formula, which basically just depends on the ionizing photon rate and covering fraction and some factor for the efficiency of converting ionizing photons to H beta photons.
Was this the 2003 Chicago request of the
Yeah, so the only point at which I'm using the ISM models explicitly, this framework model, is, that's definitely what's governing the star formation and everything. But for this model, all I'm using that for is to determine which particles have full gas. Everything else is assuming a temperature of 10 4K, and yeah, ionization from the black hole.
And so, sorry to.
It's okay.
What is the range of ionization parameters here?
I'm using it's 10 to the minus 4 to 0.1 roughly, or 10 to the minus 4.5 to 10 to the minus 1.5.
So these are just word simulations, not house models.
Exactly. Isolated mergers.
You're aiming at nearby AGN secrets, basically.
Mm-hmm. Yeah. So things like that have been observed in these SDSS surveys.
Sorry.
So redshifts of 0.1 roughly. Yeah.
Well, the small point, I guess, is that at the upper end of that ionization parameter, the radiation pressure is not variable, so you can actually reasonably whatever effect is in there, density distribution.
Yeah, so that's certainly possible that at some of the higher end of the ionization range that there are other things that come into play that we're neglecting here. So yeah, I definitely want to use some follow-up work that takes into account some things like radiation pressure and actually radiative transfer, etc. So yeah, that's a good point. Right, so once we have the H beta luminosities, then I can spit the velocity profiles for a random sightline and then determine when these systems are in double peak narrow line phases. And so to produce an observable double peak neural line, I assume that it has some minimum peak luminosity and the peak separation greater than the full width half max, so you can actually resolve it. And then the peak ratio has to be at least somewhat comparable, greater than 1 to 20. And observable is in quotes because, like I said, these simulations don't incorporate any kind of radiative transfer, and so in particular we're not accounting for obscuration by dust or the contribution from stellar polarization. So for now we're just probing the gas kinetics at a more qualitative level in this initial study. So I'll give you some examples of what the results look like from this. So here's one simulation showing the evolution of the bolometric and the H-beta luminosity in these panels, the ratio of the H-beta luminosity to the two neuron regions, and then the black hole separation versus time. And so look at the top plot first. The black hole 1 and black hole 2 are shown in red and blue, and then after the merger they're shown in green. The thick lines are the Eddington limit. The thin lines are different criteria for AGN that I've defined based on minimum bolometric luminosity. And so you can see the same color scheme for the H-beta luminosity that, as one would expect, the H-beta luminosity traces the AGN activity, so you get a peak shortly after the first close passage of the two black holes, and then you get a bigger peak around the time of coalescence. And you can see also that the ratios of these two fluctuate a lot, so I'll come back to that point more later. So I've defined, for the purposes of keeping track of when the black holes could actually be seen in this kiloparsec scale phase, I've defined different phases throughout the merger. So phase 1 is the early merger phase, so anything before they enter the kiloparsec scale phase, and in this case that's defined as somewhere between 5.5 and 21 kiloparsecs, depending on what redshift you're looking at. So it's basically the maximum separation at which they could both be seen on the same spectrum. So the early merger phase, phase 1 is anything before that. Phase 2 is when they're in that kiloparsec scale phase. 2b is also here, so this white space in here is the point at which the black hole separation gets a little bit larger than that maximum that I've set, or if both of the narrow line regions become inactive because the accretion rate dips too low, then you can also get a gap in the kiloparsec scale phase.
So what's the Gauss ratio?
In this particular simulation, it's 1 to 2. Yeah, so I'm basically looking at 1 to 3 or greater.
They're like gas fractions of 10%. Spirals.
Yeah, they're spirals. I've tested some with bulge components. It doesn't seem to matter too much. The gas fractions are initial gas fractions around 10% or less. I've done some with 30%, but that's where I start to get a little more worried about the star bursting and the dust. So I'm focusing more on the lower gas.
Sorry, can I read off this plot where you have the quote observable double narrow?
Yeah, sorry. So the gray shaded regions are when the black hole separation is correct for being able to see them in the kiloparsec scale phase, and at least one narrow line region is active. That still doesn't mean that you have a double narrow line phase. That I'll have to show you.
That's in the purple.
The purple is just when both narrow line regions are active. That doesn't mean that double. Yeah. Right. So then phase 3 is the post black hole merger phase.
What determines whether the regions are active or not? Gas happens before?
Right. So it's depending on how many particles are selected as narrow line particles. So I'm setting the minimum quite low as at 10. But almost the entire time that these are active, they have more like hundreds to thousands of narrow line particles. So
you're calling narrow line based on the radius of the black hole is where you decide. So we have this radius again.
Yeah.
How far out do you go?
it's solely set by the flux of ionizing photons, determining the ionization parameter and luminosity.
So like you don't have a wind being launched from that's pretty clear.
Right, yeah, so that's another, the whole feedback, momentum feedback issue, like you said, so that's, yeah, there's a lot of other things that could be going on.
But that would make it more visible, I guess, is what I'm saying.
If you had...
If you had a wind, you're almost always going to come around.
Sure, yeah. So yeah, this is based solely on the radiation from the black hole. So that's, yeah, that's another thing that we can put to account for at some future point. Right, so now I'll show you a little movie of what these narrow line regions look like. So I'm going to start this just before the black holes enter the kiloparsec scale phase. And so we're looking at a velocity map, basically, where the black hole's velocity is shown with the colored arrow, and then the narrow line region is shown as the smooth points. And so you'll see, you can already see in the first snapshot here that this narrow line region is blue shifted pretty obviously with respect to the mean. And so you'll see that intensify as they come through a close passage. Let's start this here. So the narrow line regions start out very diffuse as the gas densities are low. So there you have the first passage. And then as the galaxies are close to coalescence, you'll see that as densities get higher, these narrow line regions become more compact and dense. And then we'll have a couple more quick passages. You can clearly see the blue redshifts, and then they merge. And then later on in the merger, as the gas densities become a little lower again, then these will start to get more diffuse. I'll just stop it there, or maybe there. There. So you can see some of these, I'll just also point out, have a deficit of emission along the midplane of this disk-like feature, which is just due to the gas density criterion that we're setting. So some of the gas density is higher here, then you get this sort of biconal type narrow line structure. So I'll just go into that. So what we find if we focus on the kiloparsec scale phase of the evolution and look at the double peak narrow lines is that the standard picture that sort of motivated the searches for these double peak narrow lines actually happens a minority of the time, where you have two distinct narrow line regions orbiting around each other, and one's redshifted, one's blue shifted, and it creates these double peaks. So in reality, the gas dynamics play a huge role in the actual structure, and so you can have some cases where the narrow line regions have double peak based solely on the black hole motion, but even that can happen in a number of different ways. Or you can have a case in which a narrow line region on its own has some rotation feature that produces a double peak, but the other black hole, or the motion of the two black holes, is influencing the actual profile. And then you have a number of cases where the double peak narrow line region arising from one of the other systems is simply concurrent with the kiloparsec scale phase of evolution. And I'll emphasize this just because Fu et al. Recently did some follow-up work on some of these double peak systems and showed that they found some where there was a double peak narrow line in the spectrum, and then in the follow-up imaging they found that those double peaks weren't actually associated with the black. They found two black holes, but they weren't associated with the double peaks. And so they said that this was just serendipitous discovery of these black holes, and that maybe the double peak narrow lines aren't a good signature. But the thing to note about that is that the kiloparsec scale phase of black hole evolution happens during the final coalescence of the two galaxies, which is right when you expect the AGN activity to light up as the gas is being fueled into the center of these galaxies. And so the fact that you have a lot of AGN activity and narrow line activity coincident with this kiloparsec scale phase is maybe not so serendipitous after all, because it's just sort of a natural result of where these are happening in the merger. Now, whether or not the double peak feature is the most efficient way to find those kiloparsec scale pairs, that's another story, but just something to keep in mind. So I'll show you a few examples of these different kinds of signatures that I mentioned. So here's an example of a double narrow line AGN directly induced by the black hole motion. You have one narrow line region with an offset, the other with, so one redshifted, one blue shifted, and they produce a double peak. Here is the narrow line map in the same format that I showed before. I guess I didn't point out last time exactly what we're looking at here. So it's one black hole, the other black hole, and then three orthogonal projections, 3 lines of sight. And so you can see the strong black hole motion here. There is also significant rotation. So even in this case, where you have clear offsets in the narrow line regions, there's still more complicated gas kinematics going on. And then here's an example where the double peak is also produced by the black hole motion, but on a much smaller scale. So this happens just before the two black holes merge. So if you focus on this projection in particular, you can see very clearly that the black holes have a strong relative motion, and in particular, this black hole is plunging through the edge of this narrow line region. But if you look at the profiles, the one-dimensional profiles here, you see that one black hole is producing almost all of the narrow line emission, and the other is not very luminous at all. And so the double peak feature is clearly arising from the black hole plunging through this narrow line region, and you can see it in all three projections, but it's not due to each black hole having its own narrow line region in orbit around each other. So again, a more complicated picture. And then here's an example of a double narrow line produced by one narrow line region on its own in this obvious rotation structure here. But the other narrow line region is very offset. So you can, sorry, I pointed the wrong one here. This is the projection that corresponds to these profiles. And you can see that they're very clearly mutually blue and redshifted. But in one, there's a double peak feature due to the rotation. The other one is much fainter. You can see here, this is the H-beta luminosity map, and so this one is much brighter than the other. And so even though it has a very offset peak, it contributes little to the final profile. But what you have is a double peak here that's offset from the mean slightly, and solely due to the motion of the black hole. So it's influenced by the black hole motion, even though the double peak arises from one narrow line region. Similarly here, you have the same situation here, where one peak is offset, and the other is double peaked, and so you end up with an uneven peak ratio in the final profile due to the black hole motion, but the double peak itself doesn't arise very much. So here's a couple examples shown along with the stellar images that correspond to these snapshots. So here's one I just showed with the uneven peak ratio, and you can see that in certain projections there's an asymmetric morphology, and you can see the double cores in the center of these. Note that in the projection that has the most obvious double peak, the black hole separation is actually smallest, which is not unusual because a lot of these, they're not circular orbits, they're very eccentric plunging orbits, and so the largest line of sight velocities come often when they have fairly small projected separations. So some of these may be difficult to resolve if you go and try to look for a double chord structure. So some of them may be hard to identify via this mechanism.
Does he understand why you're getting double peak profiles in a single black hole?
So, I mean, it's sort of the same question as people have asked for a long time with broadline regions, right? Why are they not all double peaked, or why are some of them double peaked?
These things are not disks, so don't necessarily.
They're not disks. Some of them are disks, but yes, and the ones I was showing when they're really bright like this, they're not disks. But they do follow the rotation of the stars, the underlying stellar distribution, and so the stars, have a fair bit of angular momentum, and it's causing this net rotation of the gas.
So, but I mean, just you don't have a particularly flat structure, and the reason you get double peak disks is you're supposed to be getting a lot of emission from the capture on some of the disks.
Sure.
And this gas is giving the images because they all look particularly disky. So,
right.
So then why are you getting a double peak?
Well, but the let's see. Right. So like. So here, I mean, you have a large gradient in the velocity here, and if you look at where the H-beta luminosity is in this example, so that there is sort of a flattened structure where the emission is brightest, and so in a lot of these, I think there is sort of an underlying.
It's just n squared, or is it because of the width of the moving?
Because
how do you calculate the emission?
the emission is based on the luminosity that's coming from each H-beta particle.
And you know the number density of the particle. Right? So is it because they're dense, or is it because they're being lit up by the? I guess you put the radiation in isotropy, run off the temperature.
Right. Yeah. So it's the density.
So it's just the density.
Mm-hmm. Yeah. So a lot of these have denser structures and sort of this like.
Okay. So because of those density structures, with the sort of lack of transfer in that, then you get things like this profile.
Yeah. Yeah. That's a fair statement. Yeah.
Okay.
So, right, so I'm just going to point out this last example, the example I showed where you have a double peak profile, but the black holes have very small separation. You can't see that in the stellar image at all, the double cores. But there is a fair bit of asymmetric morphology due to the merging galaxies. And so that's another hint that maybe the situation is more complicated than the picture I laid out at the beginning, where it's not clear exactly how these stellar morphologies relate to the black hole structures, or the black hole's positions. So now I'll talk about the lifetimes of these double peak phases that I calculate looking at averaging over a number of different sight lines and looking at each phase in particular. So the first column here is kind of a complicated plot, I know. The first column is the double peak, the kiloparsec scale phase, and so phase 2. And the height of the bar is the length, the total length of the phase, so about 100 million years. And then the blue bar, or the purple bar, is when there's an observable double peak profile in that phase. And then the green and the cyan is when there is an observable double neuron profile and the volumetric luminosity meets the AGN criterion in at least one or both of the systems. So you can see that this is mostly a definition retained for completeness. Almost always when the narrow lines are bright enough to meet this criterion here, on the minimum H beta luminosity, the volumetric luminosity is also above the AGN criterion. But yeah, I have retained the distinction here. So these next few bars are the early merger phase, which is very long, which you can see the total height of the bar here. And then phase 2B, the sort of intermediate phase that I mentioned, where they don't meet the criterion for being observable kiloparsec scale pair. And then the post-merger phase is the final column. So the first thing to note is that the post-merger phase definitely dominates here, and this is pretty generally true of our simulations. And then in this example, phase 2 and phase 1, the kiloparsec scale and early merger phase have comparable lifetimes of about 10 million years. Although the early merger phase, the AGN luminosities are typically lower during that early passage than during final coalescence. And so the range of values here for averaging over different sight lines is much larger, whereas these seem to have a minimum of at least a few million years.
Why is each bar divided up into subbars?
The purple is, or are you asking about the green bars in particular?
Yeah, why 4?
Right, so the green bars are 3 different definitions of an AGN. Sorry, I forgot to say that. So the first
they all
one
get
is
the same results, so they all like.
right, yeah. Yeah, so I mean there's a little bit of drop off for the highest one is 10% of that A10 is the criterion. So yeah, so for the most part, especially in this case, this is equal mass merger, 10% gas initially, so fairly strong neuron emission. So yeah, they're all pretty much the same. So let me show you.
One more question.
Yes.
Why are the error bars so different in the different places?
Right. So so sort of what I was just saying about how the early merger phase has fainter AGN emissions in general, and so while it does the total amount of double peak neuroline emission in that early merger phase can exceed the amount in the kiloparsec scale phase. It oftentimes does not. So in general, the time right around the coalescence of the 2 black holes, so the kiloparsec scale phase and the post-merger phase are dominant. And you'll see that in some of the other models I'll show. And so in these phases here, where the AGN emission is just more spotty, then there's a lot more variation due to the line of sight.
Just remind me again, what do you mean by post-black?
Post-black hole merger. Yeah, phase 3 is post-black hole merger.
And you're still getting double peak profiles because the gas is sloshing around.
Exactly. Yeah, and the AGN is typically very bright there, so that's another reason you're getting so much there. So are there any more questions? I know this is a confusing plot, so if anyone has more questions later, you can also ask. Right, so just to give you an even more complicated thing to look at. Yeah, so don't try to focus on all the details here, but this is basically the same plot that I just showed you, but reproduced for 8 different models with equal mass towards the top, so higher mass ratio towards the top, and higher gas fraction towards the left. And so you see that, as one would expect, there's more AGN and more narrowline activity as you go to higher mass ratios and gas fractions. So here's the one I just showed you. And you can see that as you go to the lower mass ratios and gas fractions, then some of these things that I mentioned about the AGN definition on 1 or 2 being active do start to matter. So you see the cyan here more when only one of the AGN is active, etc. Then for things that this is a 1 to 3 merger with 10% gas, you can see there's very little going on here at all. So these are all, definitely major mergers with at least some amount of gas in them, some substantial amount of gas in them that produce these LP narrowline phases. And you can also see more clearly in some of these that phase 2, the kiloparsec scale phase, and phase 3, the post-black hole merger phase, do dominate over the early merger phase in these cases. So that's a fairly generic result.
So these are all different simulations, right?
Mm-hmm.
And so the higher F gas is just in the initial condition of the 2 galaxies?
Mm-hmm. Yeah. So the gas in all of these is being depleted over time due to star formation, but obviously, higher gas to start. So it's depleted by about half by the time that this is going on. And so yeah, these do have higher gas at the time of the kiloparsec phase. So I will switch gears now to talk a little bit about recoiling black holes. Just very brief overview of the basics. Gravitational wave recoil is a generic outcome of asymmetric black hole mergers, unequal mass ratios or spins, and the kick that is imparted to the black hole at the time of the merger as a result can be quite large, up to 5,000 kilometers per second as per the latest results. And if you assume optimistic things about the spin distribution, then something like a third of the kicks may be greater than 1,000 kilometers per second. If the spins are instead partially aligned prior to merger, or the spins aren't very high prior to merger, then the kick distribution would be lower. But certainly there's a possibility there that some of these kicks could be astrophysically interesting. And so the signature that has been focused on the most for gravitational wave recoil is offset AGN. So when you pick a black hole out of the system, it should carry along its broad line gas. And if it's able to ionize gas and create narrow line emission, which is remaining at the redshift of the host galaxy, then you can see a broad line narrow line offset. And if you don't excite narrow line activity, you could still see an offset broad line with respect to the host galaxy. And you could also hope to see spatial offsets in these. So there have been a number of candidates recently for both kinematic and spatial offsets. And as you can see in blue here, these all have other possible explanations. None of them are confirmed. But I will focus more at the end on this one candidate which has both kinematic and spatial offsets, which I would say is the most promising candidate to take. So just play this little movie here just to give you a picture, a qualitative picture of what's going on. 2 galaxies merging, and once the black holes come together and merge, you'll see a large kick in this direction out of the plane. And then on the right here, you can see that I have these trajectories plotted. I'll wait until this finishes. Oh, there it goes. I stopped the simulation right about here because the black hole is obviously going to wander around for a very long time before it settles back, and so we're still going to continue the simulation. On the right here, I'm showing trajectories for a range of kick speeds, scaled to the central escape speed. So the colored numbers here show the fraction of the escape speed. And the trajectories here show the different galactocentric distances versus time of the black hole. And if you focus in particular on the green, you can see here that for the top set of trajectories, which correspond to a model of 60% gas, and the bottom, which corresponds to 10% gas, there's a huge difference in the trajectories solely due to the presence of the gas. So that's the drag forces from the gas can confine these black holes to the central kiloparsec or 2 of the galaxy, even for fairly large kicks. And we also calculate accretion onto these black holes. And we allow for both bonding accretion, which is calculated in the usual way in the code. And then we also allow for accretion from the disk of gas that gets ejected along with the black hole. And so that's a monotonically decreasing accretion rate as the disk slowly diffuses outwards. And here's just an example of what that looks like in a given simulation, set of simulations. So here we're looking at the accretion rate onto the black hole in the top panels, the black hole mass versus time in the bottom panels. And each set corresponds to a different kick speed. So in the no-kick case here, we see that the accretion peaks during the first passage of the black holes and again at merger, and then quickly dies off after each peak due to the feedback. If we go to moderate kick speeds, we see that the peak during coalescence gets truncated because the black hole gets kicked out. But in these cases where the black hole is able to settle back down at later times, it has a later phase of accretion at lower luminosities. So you get this sort of third peak of accretion that's offset from most of the rest of the merger in the galaxy.
What determines the black hole kick speeds in the simulations? Like putting those in by hand?
Putting those in by hand, yeah. So my aim was to do a large parameter study and systematically probe different kick speeds. And that was a much easier way to get some idea of the trends in the behavior of recoiling black holes instead of trying to make some guesses on what's happening with the spins on sub-resolution scales. So.
Okay, so went from 0K to 5,000 kilometers per second? Or?
No, so basically from 40% to 120% of the central state speed, which ends up being something like 300 to maybe 1,600 kilometers per second.
And what are the mass ratios of these motion?
So anywhere between, so the galaxy mass ratios are sort of equal mass to 1 to 4, and so the black hole mass ratios are also comparable. So they're comparable mass black holes.
So you had a 4,000 courses that you scratched out, that's 5,000 kilometers per second.
Yeah.
And that's because the simulation is going high spin, or?
So there was this paper by Elusive and Blecha recently showing that they found this configuration that had a stronger dependence on the spin-orbit coupling, and people in this room can probably tell you more about it than me, but they found a new higher maximum of 5,000 kilometers.
Well, just a general question about the high kick speeds. My understanding is that the simulations with spin parameter 0.99 have been done yet. But so the question is we didn't even know what the answer is, but are there general principles that would allow one to say that the kick speed doesn't diverge as we go to very high spins, or there's some basic law on the kick speed?
Yeah, I don't think it's supposed to diverge because I think there's only so much energy, being emitted at the time of the merger, right? I mean,
there's a lot more energy than magnetic energy in the black hole, with 5,000 kilometers per second.
sure, but how much of that can actually be imparted to the black? I mean,
but
again, this is not my area of expertise, how the merger exactly leads to the final refocus. But yeah, my understanding is that there is.
we can ask these guys after.
We can ask these guys after, yeah. Right. So I don't want to run out of time, so I'll try to move a little more quickly. So at the higher kick speeds, the accretion gets cut off pretty sharply at the time of the merger, and there's not much going on afterwards. And you do in these cases end up with a smaller final black hole mass because it just misses out on the accretion that it would have had otherwise. So here's an example of the recoiling AGN lifetimes versus the stationary lifetimes for a given merger model for different kick speeds. So the stationary lifetimes for these 3 AGN definitions are in black, and then the cyan is the recoiling AGN lifetimes. So you see that at these moderate kick speeds, there is actually an amplification of the total AGN lifetime because of that late phase accretion that happens, but only for lower luminosities. For the brightest phase, it's always a shorter AGN lifetime than for the stationary because of that kick cutting off the peak accretion phase. So that's fairly generic behavior in our simulations.
So the difference here again is that in the recoiling one, the black hole takes this gas wave itself and then eats it up. With the stationary one, the remaining is a difference.
Exactly. Yeah, so the recoiling one has a very finite reservoir of gas for entry. So of course what we care about the most for observing these is the offset AGN lifetimes, when these could actually be distinguished from stationary systems. And so that's what I've calculated here. So we're looking at the same sort of plot, so the AGN lifetime for different kick speeds, scaled to the central escape speed. And the different colors show different merger models, separated by mass ratio just for clarity. And so the left plots show the kinematically offset AGN lifetimes for a minimum velocity offset of 800 kilometers per second. And then here is the spatially offset lifetimes for a minimum offset of 1 kiloparsec. And so you see that in all cases, the maximum lifetimes are up to tens of megayears. The kinematically offset lifetimes either occur in these higher peak cases as the black holes leaving the system, it sort of gets one shot and then its gas is depleted and gone. In these cases, at the more moderate kick speeds, if the kick is large enough and the galaxy is massive enough that it retains this rapidly recoiling black hole in the first numerous paracentric passages, then it can get this phase of Bondi accretion dominated AGN activity here. But yeah, for the higher kicks, it's just as it leaves the system and then it's done. Spatially offset lifetimes occur for a wider range of kick speeds and can have longer lifetimes, but generally at lower luminosities. As yeah, the black hole is farthest away from the system and has less gas to accrete from. So yes, to recap, these are dominated by Bondi accretion, these are dominated by the ejected disk accretion, and then the spatially offset ones can happen once it gets farther away from the system. So I'll also talk a little bit about the effect that recoils can have on their host galaxies. So in particular, here I've plotted a set of two sets of simulations on the M-sigma relation. So the black points show the M-sigma relation for a set of simulations with no recoil kick. And then the red points show the relation for high kicks. And so this is not in any way meant to reproduce the local M-sigma. This is not a cosmological simulation. I've varied the parameters in a very systematic way. And moreover, these kicks, these high kicks aren't actually going to bring a lot of black holes to come back any time soon. So you could have even more scatter induced because another black hole with a different mass would be brought in due to subsequent merger. But what you do see is the relative difference solely due to having a high kick versus no kick. And so there's a downward offset because, as we saw, the recoils lead to mass deficits in the black holes, and an increase in intrinsic scatter. And so that's a fundamental result of recoil because normally, if you just have a stationary black hole, the final mass is set by how much gas is driven into the center during the merger. And if you have a recoil, then you have an additional free parameter, which is when exactly the kick happens in relation to that gas being fueled to the center. So there is an intrinsic increase in the scatter solely due to that.
Is that bigger scatter consistent with this observation?
So that is a much trickier thing to say because it's very difficult to disentangle, the components. So the increase in scatter here is a factor of about 2. But the no kick case here has much smaller scatter than the actual M-sigma because we're using one feedback efficiency and there are a lot of things contributing to scatter. So
but that's what I'm asking. If you take some reasonableness with these other.
Yeah, I would say it's definitely consistent. We're not seeing crazy huge scatter. So I think it's definitely consistent. But in terms of actually how much it contributes numerically, quantitatively to the relation, I think that would be very hard to say. So in addition, you can see an effect in the central cusp of stars solely due to the removal of the AGN feedback when you kick the black hole out. So here we're looking at the star formation rate versus time for a simulation with no kick in black, simulation with high kick in red, and a simulation with no black holes at all in blue. So you can see that after the merger, which is shown in this vertical line here, there is an increase in star formation rates in the case where the black hole has been kicked out, almost as if there are no black holes in the entire simulation. And that's solely due to the removal of the AGN feedback. And here we're looking at the stellar profile in the final remnant. And so the old stars are shown here with these lines, the same color scheme, for the same simulations, and the new stars are here. So the new stars dominate within the central kiloparsec or so. What you can see is that in the very central region, there is an enhancement in the final density, a factor of about 2, for the recoiling black hole over the stationary black hole. So you get a denser and also more massive stellar cusp and remnant due to this recoil.
So is that why your sigmas were moving to the right a little bit in the previous?
Yeah, so there is a tiny effect on sigma. Almost all of what you saw in the sigma plot was due to the black hole masses, but there is a very small sigma effect too. So I know I don't have a huge amount of time, but if I can take just a couple minutes, I'll talk about this candidate, which is very exciting. So this system was originally serendipitously found in the Cosmos survey. Its HST image shows this spectacular tidal tail and these two resolved bright optical cores in the center, and separation is about 2.5 kiloparsecs. So this was initially proposed to be a supermassive black hole pair, especially since this spectrum showed sort of a double-peaked substructure in the narrow lines. And the only problem is this is a very low signal-to-noise spectrum, and very high spectral resolution, but low signal-to-noise. So it's unclear whether this is just consistent with the noise. And that was what was proposed by Blecha et al. When they found these other spectra, which had lower spectral resolution, but higher signal-to-noise, and showed a clear offset between the narrow and broad H beta. And so they proposed, and so this offset is 1,200 kilometers per second. And they proposed that this is actually a recoiling black hole. This is the signature I discussed before for that. So this is the same HST image with a Chandra image imposed over it, which is completely unresolved for the central two sources. But recently, they have high-resolution Chandra data, which shows that almost all the emission, good significance, is coming from this southeast source. So here is the HST image with the old Chandra image in green contours and the new in black. And so you can see that it is all coming from here. So this doesn't prove the recoiling scenario, because this could be a quiescent black hole. If it's an obscured black hole, it would have to be very quantum thick, extremely quantum thick. But it could be quiescent. But certainly the fact that the AGN is only detected in X-rays here is consistent with the recoil scenario.
So what is this galaxy like? What's the start mission?
It's pretty high. It's an upper limit of 100 solar masses per year.
So obscuration wouldn't surprise you.
Obscuration wouldn't surprise you.
What's the ratio?
0.3 something, I think. So yeah, obscuration would not be good, but I mean, you know, this is a hard X-ray.
What is the broad line region? You got a spectrum.
I mean, no, so they have, I think, 3 spectra which show this broadline neuroline offset in the H beta. But I don't think they know anything else about the broadline. So what I've been doing is trying to constrain the parameters for the recoiling scenario, if this is actually a recoil, compare that to the black hole pair scenario. So this is the best fit model I came up with in trying to reconstruct the system. And then I picked a black hole such that it would have the right separation and the right line of sight velocity, and figured out what at what time and what the AGN velocity would be at the time of that observation. So the peak velocity is somewhere between 1,400 kilometers per second, and it can go anywhere up to 2,500 kilometers per second, just to generate the time of observation. So basically, it has to be a major gas merger. The time since the merger to observation is a few mega years, and then the black hole mass, star formation rate, and the Eddington ratio of a few percent are all consistent with the limits from the observations. What's not clear is if this black hole is too far away to produce the narrow line emission at the time of observation, but it's not clear yet if the narrow lines are coming from this source or from this source. So it could just, the narrow lines could just be stellar in origin. It's not clear yet. So certainly, the jury is still out. It's unclear what's going on here. but it is consistent with the recoiling scenario as far as I can tell. So,
So you have 2 points of, well, 2 hazy sources on the left hand side. Are they both, do they both contain stellar clusters, or you don't know for sure?
I mean, we can't say for sure. So the surface brightness decomposition that was done in this system fits this northwest source, which is allegedly the stellar cluster, with a Sturzik profile, and the southwest source with a point source. That was the best fit surface brightness. So it's consistent with being a point source, but
Is the southeast one really blue?
you know, I'm not sure about the colors. I mean, I mean,
Because the argument is it's an AGN.
Right.
And you're seeing continuum, which could be very blue.
yeah, yeah. I'm not actually sure about the colors. I don't know if there's any obvious difference between the two, but I've been asking. So yeah, that's all I'm going to say. So if anybody has more questions.
The main reason for the picking of at least the southeast sources of AGN is the X-ray emission. Is that right?
Yeah, along with the offset, which is, I
Well,
mean,
you could have two nuclei, I guess.
you could have 2 nuclei in merger. The offset could not be due to their relative motion because it's too big. The offset could be
Or
due.
the velocity offset.
Yeah, velocity. Oh, sorry. Yeah.
The velocity offset's between a narrow line and a broad H beta line. And, you know, as I say, a lot of these narrow lines nearby, it's clearly optimized.
Yes.
It's good backside to see the evolution. Or
The narrow line itself is.
the narrow line can be shifted compared to the broad line, so then it's still possible.
But not by 1,200 kilometers per second.
Narrow line is 3,000 kilometers a second.
Well, this one's a lot narrower than that, right? So
Say again.
the width of this narrow line is a lot narrower than the offset between it and the broad line. So
Right, but
that puts constraints on how.
well, it depends on the orientation that the narrow lines are coming out of. Because normally you see both sides, both cones, both orientation cones.
Mhm.
But this thing has a lot of gases. So which way is the relative offset from the broad line and the narrow line? Is it
The
the narrow line is to the two part of the red?
The broad line is redshifted, so the black hole is recoiling away from the.
Well, ultimately the narrow line is evolution, which is what you'd expect that this thing we're seeing nearly face on, which goes like this. And the narrow line is coming out at us.
Right, but I think the narrow line is consistent with the redshift for the host galaxy.
Based on what other line?
Based on, I have to check, but,
Normally people use some narrow line, you use
Right.
passage 2 line,
right,
but you get those out of the narrow line too.
right, yeah, and I mean, there might be some solar absorption, I'm not sure, but yeah, so that, yeah, you know, that's the observers.
So you showed a plot with the FC relation with V equals 0 and V equals 0.9 in this case. So you sort of adjusting the feedback physics. Did you use the M sigma relation? I mean, I'm trying to.
That was adjusted a
Yes,
long time
and,
ago.
yeah, exactly.
I
I didn't
zero
adjust
case.
anyway,
But then in practice, that's what really happened. And then you
Yes.
said then the V equals 0.9 calculation was done with the same input.
Exactly, so
assumptions
the only
to
thing
see
that I
how
proposed to
how the
infer
velocity-
from that plot is the relative difference between those 2 sets of data.
And then the last question I have to do with bouncing black holes. We have lots of bouncing black holes
Yeah.
in the sort of range of V. But in the accretion streams, you didn't see any bouncing ever. So basically the gas goes away and so you only get the first accretion basically in the first bounce.
So here is where you can see the bouncing black holes. So in these moderate Higgs speeds, where you get this later phase of accretion, that's when the black hole is oscillating about the center. And so, especially here where the oscillations are larger, the slightly different speed, you can see that there's a lot of noise here because you're actually just picking up bits of accretion on each paracentric passage mostly. And so it's all blurred together because this is on a time scale of almost 5 years. But that's exactly what's happening here. Is you're getting this accretion happening while the black hole is making these numerous paracentric passages through the center on short time scales.
So while you're on the subject, what are your halos like? Are they W profiles or are they IC?
They are printless. Yeah.
Because it does actually make a difference, this bouncing times. Right? If they're isothermal, then they sort of really hang out a long time before they come back in. And real halos, you're going out to like 100 kiloparsecs or not much farther.
Yeah, something like that. So let me go back to the trajectories here. So
Yeah, most of them are inside on the hollow side.
But some of those
Yeah.
are very long bugs still, which is why I was asking.
Well, I'm saying you need a longer one. Because see, they're using two cores. I mean, real galaxies are isothermal, so out to 50 or 80 kiloparsecs, despite what benefit. So that would mean the balance kind of is a lot longer than what you said.
yeah, that could be.
It'll sort of exaggerate this effect that Chris is talking about.
Well, but you're dealing with the result of the merger now. So
You have
guess
the mergers and spatial-offset.
Well, I mean, there is a
in
relaxation.
your
time.
simulation, you describe the initial conditions like that for your two merging galaxies. But after the merger, what is the mass profile look like?
I mean, it looks much more like an elliptical. I don't think I.
But that's
So
the question.
electricals are also isothermal.
Yeah,
Right.
The question is,
Yeah, but I
does the dynamics actually give what you're describing?
It might, yeah, it's possible.
I mean,
Yeah.
you don't care about the initial conditions are really what we have on what happens up.
yeah. So that's a.
Well, but it's not, no, but remember, we're talking about profile on larger radius, what, 10 to 50 kiloparsecs, and that's not going to be changed that much.
But once you get to the orbits that are going out to those radii, I mean, this could orbit for a very long time, indefinitely basically anyway. So
Right.
whether it has slightly longer orbits or not, I think is a mostly moot point.
Well, but I'm even worrying about between 1 and 10.
Okay, so yeah, maybe then there could be an issue with that, with like this type of profile.
It just make Chris's point more, go to the cut off, go to the whole bit, spread out here and see.
Yeah. Well, and like I said, there's also going to be more scattering introduced because these big picks, are just going to be replaced by new black holes brought in by subsequent mergers, and those could have whatever mass. So there'll be scattering.
It's just a general question. It's just not going to be like, people talk about 1,000 kilometers per second. It's not just the whole galaxy. But we know, right, when you look at like this, when people look at voltages nearby, you always see black holes.
So
It's
yeah.
zero order, right?
Yes, but I mean, the number of galaxies for which we can actually measure the fact that there's
It's
black
about
holes.
50 or 100.
Yeah.
Statistics are getting pretty good.
Yeah, exactly.
That's asking a good question of
Yeah.
But
function.
that's-
The issue is what kick speed, what typical kick speed,
I think-
upper limit can you then set, right?
So
Based on your, based on your
Oh
work.
yeah, typical kick speed should, I would say, is very safe to say that that's hundreds of kilometers per second. If that's typical.
A few hundred.
Well, if you get up to above 400, it's pretty dark.
So the kick speed depends the zero port on the mass ratio and on the
No,
spin direction.
you're telling us about the theory. We can actually
No, no,
see
but-
the damn thing. We don't have to worry about what you have.
Right, but it's only based on their merger
And so
history.
I'm telling you, this will tell you about the mass ratio and about the spin direction of the merging black holes.
Right, so I think the fact that we see the black holes at low redshift is a comment on the fact that there are not a whole lot of equal mass mergers between massive ellipticals at low redshift. And so, at higher, there's minor mergers aren't going to give you very big picks, and mergers at higher redshifts certainly should happen, and maybe there's some of the ones we can hope to see, at the intermediate redshifts. But at low redshifts, they should be replenished by the black holes, or just, be minor mergers that give you little picks. So I'd say that those are very safe statements, and I don't see an inconsistency with the fact that we see those black holes at low redshifts, and the possibility of, maybe finding a recoiling AGN somewhere, SDSS or whatever, cosmos. Not that it'll be easy, but.
It's good, discussion upstairs.
Yeah.
Thank you, Laura, again.